let's get started. All right, it's a great pleasure for me to be here today at the APS March meeting to share my research. It's also a great pleasure to follow someone from Northwestern University from the Chris Wolverton's research group, because I did my undergraduate research in Chris Wolverton's research group a long time ago, back in like 2008, 2009. So it's a lot of fun. And it's a really great lead in to the topic that I'm going to talk about today, which is evaluating synthesis and synthesizability beyond the DFT convex hull. So new metrics that we can use to quantify synthesis and synthesizability. Before I get started, I'd just like to thank the organizers, Professor Gervois Hautier and Dr. Sinead Griffin for inviting me to give this talk today. And so since this is the session on the computational design and discovery of new materials, I think everyone's very familiar with the ultimate vision of using high throughput DFT to accelerate materials discovery, right? Density functional theory today, just as the last speaker showed, has become so computationally efficient that we can, without exaggeration, calculate the properties of nearly all known inorganic materials and generate new structures based off of them. And the dream is that based on which properties we might want for certain technological applications, we can screen certain databases. The Materials Project is a database that's run through UC Berkeley, and we can screen for different materials that have properties that would make superior technological materials, right? The traditional materials design process when you do this is what we call a sieve. And in this sieve, you take the list of known compounds and you calculate a variety of properties of these compounds. For example, band gap. In this particular paper, they were studying the water oxidation and reduction potentials. And after you down select this 100,000 list of materials down to 30 or so, you can hand it off to our experimentalist colleagues. They can go synthesize it, characterize the performance, and we design new materials. So early on in these sieves, and this always happens in the computational materials design process, we assume that we want materials that are sieved to have a delta H less than 80 MeV per atom, or some relatively small number. And what this number refers to is the stability with respect to the convex hull, right? As we know from Gibbs, the convex hull is the lower energy convex envelope that connects the elemental reference states. And materials that fall on the convex hull are considered stable, and materials that have an energy above the hull are considered metastable, right? So let's talk a little bit about stability and metastability and how we can use this to influence materials design. So we know that most materials that we encounter in the world are convex hull stable, right? However, we also know that there are many materials that are convex hull metastable that can be synthesized and are often very useful, right? So some examples like were discussed earlier, diamond carbon, anatase TiO2 is an interesting metastable TiO2 polymorph that's good for catalysis. Yttrium barium copper oxide, very famous superconductor material, is also DFT convex hull stable. In 2016, I published a survey of thermodynamic metastability based on the Materials Project in Science Advances, and I showed that 90% of known metastable materials have a DFT energy above the hull less than 70 MeV per atom. Okay, and 2 years after that, we also published that 100% of known metastable materials have an energy above the hull lower than what we call the amorphous limit. So if you go into DFT, you use ab initio molecular dynamics and you amorphize a unit cell, all crystalline metastable phases have an energy lower than that amorphous structure's enthalpy. Okay, so based on these known facts, a lot of people in our community have followed what we call what I call the synthesizability assumption. And the synthesizability assumption is that stable materials, delta E above hull equals 0, are synthesizable, that metastable materials that are close to the hull are probably synthesizable, and that if you have a material that is much higher in energy above the hull than that, then it would be risky to pursue experimentally. And this is kind of the assumption that our community has adopted, which I think many of you in the audience are probably familiar with. These synthesizability assumptions are pretty good. You can use this to do a lot of exciting materials discovery. So here's a paper that I published last year. This is how we use DFT convex hull to drive ternary nitride stability. In fact, using the data mine structure predictor as described in the last talk, here we took known nitrides, we did substitutions, we found a lot of new nitrides. The innovation here is not really the substitution aspect and finding new materials, but really how do you visualize stability space, right? So we constructed here a map that clusters different elements together that have the same propensity to form ternary nitrides. And so here, like metal 1 would be the row, metal 2 would be the column. So each square represents a ternary nitride space. Inside each space, there is a full ternary phase diagram. You can access and explore the entire ternary nitride space at my GitHub website here. And okay, so what we've done here is we have predicted every single purple box represents a new stable ternary nitride space. Guided by this map, my experimental colleagues at NREL successfully synthesized 7 new ternary nitrides within 1 year, so very fast discovery rate. And these were published in a very nice journals, and they showed a lot of very interesting behavior in ternary nitrides that had not been previously known. Okay, so this approach of using convex hulls to evaluate stability is a good guide for experimentalists. And there are success cases. Here are some cases that we did not publish, okay? We also had experimental colleagues who tried yttrium rhenium nitride, antimony nitride, and manganese 3 and 4. These did not violate the synthesizability assumptions that I showed earlier, but we could not synthesize these materials, okay? And you know how it is. We try to synthesize it. If it doesn't work, it's like a waste of time. You don't really publish these. Recently, people have become more bold in publishing failed synthesis experiments, okay? Here are 3 that I think are very noteworthy. This is a paper published in 2016 from Professor Shoemaker and Professor Wagner from UIUC. I'm just going to read the section that I think is relevant. We perform a systematic combined theoretical and experimental search over ternary phase diagrams that are empty in the ICSD, containing cations, transition metals, and 1 selenium or sulfur, so look for sulfides and selenides. We then conduct a variety of synthesis experiments to check the candidate materials for stability. While the prediction method did obtain previously unknown compositions that are predicted stable in DFT, none of the candidate materials formed in our experiments. Okay, convex hull stable materials that did not form in their experiments. Here's another paper where they said, we also attempted to synthesize lutetium fluoride in this particular structure, which is predicted to be only 7.7 kilojoules per mole above the convex hull. That's 7 MeV per atom about. This attempt was unsuccessful. Okay, not that metastable, only 7 MeV per atom, still cannot be synthesized. This is a very recent paper searching for new ferroelectric materials using high throughput databases, an experimental perspective on bismuth aluminum oxide and bismuth indium oxide. Here we report the experimental evaluation of 2 such predicted candidate ferroelectric perovskite oxides, bismuth aluminum oxide and bismuth indium oxide. Despite exploring a wide range of temperatures, pressures, substrates, laser fluences, and so on, attempts to grow bismuth aluminum oxide with this approach resulted in no perovskite phase. Okay, so materials that are predicted to be stable or low energy hull metastable often cannot be synthesized. Okay, and I came from the Sater group at Berkeley, previously at MIT, and just to let you know, we've been predicting a lot of materials over the years, and probably 50%, this is our estimate between me and Professor Sater, we estimate that about 50% of the materials that we predicted that should be synthesizable by that synthesizability assumption could not be made. Okay, so this is a dire bottleneck when it comes to computational materials design, right? We're predicting, like the last speaker showed, we can predict tens of thousands of structures, but if you cannot synthesize them, even after going to the laboratory with expert chemists, first of all, it's very frustrating, and second of all, it kind of makes us theorists, look bad, right? We're sending people on wild goose chases, and I'm speaking from experience. I've done this, and people in this room may have done this as well. So I think that 3 of the really important questions, and Vladan at the beginning of this session also mentioned some of these, 3 of the really important questions that it comes to synthesis and synthesizability are, here's my perspective. Number 1, which predicted compounds are synthesizable? Okay, which compounds that we design in computation can be synthesized? Number 2, which synthesis method is best to synthesize it, right? There's a variety of different types, hydrothermal synthesis, solid state synthesis, pulse laser deposition. Which synthesis method should I use to synthesize my predicted material? And within that method, what synthesis recipe, in terms of like parameters and conditions, can lead to a phase pure synthesis of the predicted compound? These are 3 extremely important questions that, to the best of my knowledge, no one today can really solve. And just another bit of my idea is that, DFT is really good at doing structure property relationships, but there's no Schrödingerian equation for synthesis or synthesizability, right? And so we have to be a little bit more thoughtful about what we are doing when we use the convex hull to evaluate synthesis and synthesizability. And mostly, I think, is that we have to revise the synthesizability assumption, okay? This synthesizability assumption clearly is incomplete, and we need to find a better way to evaluate synthesis. Okay, so the first thing I want to address is this idea that a low energy above the hull being a sufficient condition for synthesizability. And this is this paper that I published in 2016 on metastability. So we took 5 very common binary oxide materials, and what we did was we calculated the relative energy to the hull of the different observed polymorphs in these 5 very common oxide systems. And indeed, we find that the observed binary oxides have an energy relatively close to the hull, right? Within about 100 MeV per atom for oxides. What was kind of surprising was that when we started calculating hypothetical polymorphs, now these are polymorphs that have known crystal structures, but not for that chemistry. So just to give an example, zinc oxide, observed structures are rock salt, zinc, flint, and wurtzite. Cesium chloride and nickel arsenide are known prototypes that zinc oxide does not form in, but we can calculate their energies in DFT. And we do so, and we find that hypothetical structures have an energy window that is oftentimes within the observed energy spectrum of the observed phases. Okay, so what does this tell us? There's 2 possibilities here. First probability is that there are still more TiO2 polymorphs waiting to be synthesized. There are about 40,000 papers on TiO2, so TiO2 has been synthesized so many times in nature and in the laboratory. And so we found it to be a little bit unlikely that there are so many TiO2 polymorphs still awaiting experimental discovery. And so therefore we took the second option, which is we think that not all predicted low energy metastable phases may be synthesizable. And like Baden said earlier, there are probably energy basin arguments for this as well. And I'm going to share a different perspective on top of that one that complements that idea about what metastable phases might be synthesizable. Just to talk about this assumption a little bit further, it's actually kind of a classic logical fallacy, right? Which is like if P, then Q, if Q, not necessarily P, right? So like all horses have 4 legs, not all animals with 4 legs are horses, right? All metastable materials that have been synthesized have an energy above the hull less than 70 MeV per atom, but not every material that has an energy above the hull less than 70 MeV per atom can necessarily be synthesized, right? Okay, so what does imply synthesizability? And this is going to be the bulk of my talk today. Before we do that, I kind of want to just take a step back and just ask, what does stable mean? Such a basic question, right? What does stable mean? Okay, first question, is iron stable? Yes, iron is on the convex hull, right? Is iron stable in the rain? No, right? Iron would be unstable with respect to iron oxides, iron hydroxides, with respect to rust, right? Is diamond carbon metastable? In DFT, yes, it has a energy above the convex hull. Is diamond carbon stable at high temperature and high pressure? Yes, right? It is stable under applied thermodynamic conditions. If you go back and read Gibbs, 1878, read Gibbs on the equilibrium of heterogeneous substances, Gibbs actually makes a very strong distinction between stability and equilibrium, okay? When Gibbs talks about stability, which is what we talk about today in convex hulls, stability is about stability against self-separation. In a single-phase homogeneous substance, the free energy must be convex up in the extensive variables, or else a compound will self-separate by extent into its constituents, right? This is kind of like the Spinodal decomposition curve. If I have something like this, then this phase will phase separate into this phase plus this phase, right? This is on the n axis, but it's also true in the volume or the entropy axis, right? The equilibrium phase is something different. Equilibrium phase is the lowest free energy phase under a certain applied thermodynamic condition, okay? And when we talk about free energy, we have to talk about boundary conditions and natural variables, right? So internal energy has natural variables of S, V, N, and all the extensive parameters. When you take thermodynamics in grad school, you learn that T and P are usually more convenient experimental parameters. So we do what's called a Legendre transformation to take U from S and V to G of T and P, right? So we make a Gibbs free energy where the Gibbs free energy has natural variables of temperature and pressure. These are new intensive natural variables for experiments, right? The important thing is you don't have to do thermodynamics using the Gibbs free energy. Okay, you can actually do thermodynamics using any sort of thermodynamic potential that you want. And besides temperature and pressure, there are a variety of forms of thermodynamic work that real materials today leverage to achieve their functionality and that we don't usually consider, okay? So, the title of my slide here is what thermodynamic handles besides temperature and pressure are operative during synthesis. You can have stress strain, surface energy, electric polarization, magnetic polarization, charge transfer, chemical electrochemistry. There's so many ways that we can push on materials that we don't consider when we're talking about the Gibbs free energy. Okay, so what we really want to start to push you all to think about is phase stability as a function of all these other parameters. Now, if you start doing so, this lays a foundation for new classes of phase diagrams. What phase diagrams do we have today? Like temperature, pressure, and temperature composition, right? Those are like the two phase diagrams that make up 95% of all the phase diagrams today. But the foundation, the geometric foundation for phase diagrams is universal. It doesn't have to be TP or temperature, entropy, or PV, right? In any extensive natural variable, even like strain or whatsoever, you will have convex hulls, right? Convex hulls where the lowest free energy phase can have phase separation, where the phase fraction is given by the Lever rule. If you have an intensive natural variable, you take what's called the Legendre transform, which gives you the dual expression. Remember, if you read Callan, you'll see that there are the dual envelope planes. And so you go from a convex hull to the dual, which is the inner half space envelope. And so the inner half space envelope is here's alpha phase, beta phase. So you take the lowest free energy phase in this sense. And this geometric foundation can give you new phase diagrams, which might give you a different perspective on equilibrium for material synthesis. Okay, let me show you. So here's the first phase diagram that I'm talking about. We all know that water expands upon freezing, right? So what happens if I put water in an indestructible constant volume container and I bring the system below 0 degrees C? What should happen? Well, water's going to try to turn into ice, but it can't expand, right? Because there's a constant volume container. And if I look at the pressure temperature phase diagram, it's really not very helpful because I don't know what pressure the system's going to be at the end, right? So, the proper way to analyze this is that water cannot transform completely to ice. Some ice will form, the ice will pressurize the rest of the water, and you'll have a mechanical equilibrium between the pressure of the water and the ice and the chemical free energy of transformation, right? So you'll have two-phase equilibrium. If I look at this phase diagram, no two-phase equilibrium, right? This is not just a thermodynamic exercise, it's actually very important from biophysics. There's this interesting fact where if you take an organ and you store it at 3 degrees Celsius, it'll decompose in 4 hours. But if you store it at -3 degrees Celsius, it'll decompose in 96 hours. So if you can store organs at -3 degrees C, you can resolve the organ donor crisis. And so what people do is they take an organ, and instead of putting at -3 degrees C, which will generate ice crystallites throughout the entire membranes and rupture your material, they put it in an isochoric chamber. They put an ice nucleation site, and you bring it below 0 degrees C, and now it forms this two-phase equilibrium. So all the ice forms down here, and all up here is liquid phase, and so your organs are not disrupted. Okay, so let's do this using the thermodynamic geometry I was talking about. This is with my colleague Matt Powell-Palm at UC Berkeley. In Gibbs free energy, the lowest free energy phases look like this, right? You take the Gibbs free energy and you take the lower projection. I can do a Legendre transform to a natural variable of volume instead of pressure. Now I get a convex hull in the volume axes, okay? That's what it looks like over here. I can project that convex hull onto the T and V axes, and there you go. Now I have a two-phase equilibrium between volume and water. The tangent lines, partial F, partial V, that's the pressure. So I can get the pressure in the system as a function of temperature and as a function of the specific volume. Okay, so this is a new phase diagram. Here's another new phase diagram. Like I said, I work on nitrides a lot, and consider here that in a lot of nitrides that are known, like binary nitrides, the convex hull looks something like this. You have a lot of nitrogen poor nitrides that are stable, and in these structures you have what's called an intermetallic nitride. It's not really an ion, it's just kind of like a interstitial nitrogen, kind of like a carbide, like iron 3C. Okay, now a nitrogen-rich nitride exists, it's just metastable, it's above the convex hull. And it's metastable because N2, triple bonded nitrogen, is so stable, it comes down, right? But if I can crack nitrogen into atomic nitrogen, I can elevate its chemical potential, and now I can generate a new convex hull that is stable with respect to nitrogen under elevated chemical potentials. I can generate the convex hull, and I can also do this experimentally. Again, my colleagues at NREL, they do plasma cracked nitrogen. And when you deposit nitrogen onto a surface like copper, well, if you're really far away, the atomized nitrogen will recombine into N2 by the time it reaches the substrate. And so, the triple bonded nitrogen is not going to react. But if you reduce the target substrate distance, now you have atomic nitrogen interacting with the substrate, and you can actually synthesize copper 3N, which is 200 MeV per atom above the ground state, a remarkably metastable binary nitride. Okay, and using this technique, you can benchmark plasma cracked atomic nitrogen to +1 eV per nitrogen. And so you can see that you can use this to access metastable phases very rationally, right? You can use an applied thermodynamic condition to target very specific types of metastable materials. Next example I'm going to talk about is solid aqueous phase stability, okay? There's a type of phase diagram called the Pourbaix diagram. The Pourbaix diagram plots the equilibrium between dissolved aqueous ions and solid phases. So this is the Pourbaix diagram for manganese oxide, and it's being shown as a function of the redox potential in solution and the pH. Now, the way that Pourbaix diagrams are usually calculated is you use the Nernst equation and calculate phase boundaries. What I did recently is I took the Legendre transformation of the Gibbs free energy to what I call the Pourbaix free energy, which adds a free energy axis to Pourbaix diagrams. And now that we have a free energy axis to Pourbaix diagrams, now we can start to add other forms of thermodynamic work to see how that changes phase stability, okay? And so, this is the whole theme that I'm going for. So let's try to make nanoscale Pourbaix diagrams. We first take a Pourbaix diagram that we already knew existed, and now I can add, since it's all in terms of energy, I can add the gamma A term, gamma A surface energy times area, right? Well, it's really area per mole, so you can do area per mole, but then area per volume times the molar volume. Now, look at this, A over V, that's 1 over R, right? 1 over R is basically a size axis. So I can take a slice of the Pourbaix diagram, fix the redox potential at some value, and then project a nanoscale Pourbaix diagram. Now I'm projecting the whole thermodynamic potential along the pH and the radius thermodynamic axes at fixed redox potential. And look at this. A variety of metastable manganese oxides are stabilized at the nanoscale. Why? Because they have low surface energy. Okay? These materials have very low surface energy, so at the nanoscale, where surface energy dominates, these materials become size stabilized. So metastable materials can have equilibrium regions under different thermodynamic axes that we don't usually anticipate. Here's another example. These are two manganese oxide polymorphs, pyrolusite, which is the equilibrium phase, and then hollandite, which is a metastable phase. Now, hollandite is metastable, but if I put it in a solution where there's a lot of potassium ions, potassium's like this big fat ion, right? And potassium cannot fit into the pyrolusite holes, but it can very happily go into the hollandite holes, okay? And so I can create a new thermodynamic potential that includes that by a Legendre transformation, and I can have now a mu K, which is the chemical potential, which is the concentration of potassium in solution. I can create a new convex hull. Take a look at this. Beta MnO2, if I add potassium in the system, beta MnO2 does not increase very much in energy, but alpha MnO2 becomes very stable when it incorporates some potassium. Okay, and so now I have another composition-dependent Pourbaix diagram that has other metastable manganese oxide polymorphs that appear on these other thermodynamic axes. You're starting to see that thermodynamics is intrinsically a very high-dimensional object, right? We started with G of TMP. I did a Legendre transformation to add pH and redox potential as a new thermodynamic parameters. Then we added mu K. This is the concentration of impurity ions in solution. We added surface energies, so you got size. And you can now take this kind of like this four-dimensional space and project it onto size and composition while retaining some pH and redox potential. And so what we're seeing here is a kind of the size axis is kind of a proxy for nucleation and growth. And we gave this phase diagram to my experimental colleagues at SLAC, which is Stanford Linear Accelerator, it's a synchrotron radiation light source. And what they did is they prepared aliquots, like little tiny hydrothermal synthesis vessels. They put it in the beamline and at these various potassium conditions, and they saw a phase progression in situ in the beamline that very much matched what we were predicting from calculation. Here's our calculated phase diagram, and experimentally what they saw was delta prime, delta double prime, gamma prime, and beta. These primes indicate a disorder. You know, we don't calculate disorder in DFT, but you can measure disorder in experiment. But we can see that the phase progression very much matches the calculated phase progression from DFT. Okay, so what I'm trying to show you is that materials that we consider to be metastable can be stabilized under some thermodynamic condition that we weren't previously anticipating under the Gibbs free energy. Okay, so I've shown a series of new phase diagrams. I'm going to show you one more that I think is a lot of fun, which is the electric field. There's a polymorph of calcium carbonate called Vaderite. Okay, Vaderite shows up in the intermediate time regime. And so, you know, just like the manganese oxide, maybe Vaderite has a very low surface energy, right? I calculated the surface energies of Vaderite versus calcite using DFT with surface energies and hydration. Now, Vaderite has a higher bulk energy. So if it forms first, we would expect a lower surface energy for Vaderite, but actually Vaderite has a higher surface energy. So what's going on there? Well, when we did these calculations, we assumed a certain wolf shape, a wolf construction using low index surfaces. Maybe we're missing some high index surfaces, right? So let's take a look at the experimental morphology to see what's happening. Well, that doesn't look like that doesn't look like a wolf shape at all, right? You got these little spherulites going on. Spherulites have a very fascinating growth physics. Okay, here's the growth of spherulitic fluorapatite. This is not Vaderite. This is a different material, but it starts off as these kind of hexagonal prisms that we were seeing previously, and then it starts splitting like this, and it splits into what's called a dumbbell broccoli. And dumbbell broccoli turns into this closed spherulite shape until you finally get spheres. Now, what's driving this very unusual and interesting growth process? If you look at the fluorapatite crystal structure, it has alternating planes of 4 plus, 4 minus, 4 plus, 4 minus in the C direction, which results in a net dipole. And so when you have crystalline seeds of fluorapatite, like the hexagonal prisms I was showing earlier, it will actually form electric field lines in solution. And when you have growth, either ion by ion or primary particle growth, it'll grow along those electric field lines, which is what causes that dumbbell splitting and causes that spherulitic morphology. And if you look at Vaderite, Vaderite has the exact same motif, which is 2 plus 2 minus 2 plus 2 minus. So it also has a net dipole, and it also has a morphology that's calculated to be very similar to fluorapatite. And what we can see is that if you look at the final spherulite morphologies, indeed you get that kind of crack in the middle, which shows this spherulitic growth. Kind of fun. But let's get down to the thermodynamic potential. What happens if you grow calcium carbonate under an applied electric field? Okay, so we take the Gibbs free energy, which has natural extensive variables for polarization, and then you do a Legendre transform to minus PE. And now I can make a new phase diagram that has electric field as one of the thermodynamic axes. Okay, and you can see that Vaderite is stable with respect to calcite under applied electric fields. And in fact, this has been experimentally validated, but not rationalized. It's been shown that electric fields can make Vaderite under electric field, but it didn't explain why. Okay, so I'm trying to wrap this up right here. The general idea that I'm trying to propose is that there are a variety of thermodynamic handles that are relevant in synthesis that we do not usually consider. These can be size, epitaxy, stress strain, electromagnetic fields, et cetera, and if we build phase diagrams that use these alternative axes, a lot of materials that we consider to be metastable are actually stabilized under certain conditions when you take into account these additional thermodynamic variables into place. And so we came up with this principle that we called remnant metastability. This is something that I wrote in 2016 in that metastability paper. And this is that observed metastable phases are generally remnants of thermodynamic conditions where there were once the lowest free energy phase. So in that figure that I showed earlier with the blue circles and the red crosses, the beta phase is the lowest free energy phase under some applied thermodynamic condition. But maybe this red cross, which is a low enthalpy polymorph, cannot be synthesized because it is not the lowest free energy phase under any condition that we've tried so far. Okay, and so this might explain which materials are synthesizable. And if you believe in remnant metastability, then this actually gives you a design parameter for synthesis. We should specifically target materials that are stabilized by what we call the extensive advantage. The extensive advantage being, if you want to synthesize, for example, a high entropy phase, you should, which is the highest entropy material, you should use high temperatures, right? Use the intensive conjugate variable to the extensive advantage of your target material. If you want to synthesize a low volume polymorph, you should use high pressure. These two are kind of obvious, right? But if you want to synthesize a nitrogen-rich metastable nitride, you should use the intensive conjugate variable, which is high nitrogen chemical potential. If you want to synthesize a polar polymorph, you should synthesize it under applied electric fields. And if you do that, if you can identify a synthesis method, there are so many different types of synthesis methods, right? If you can identify a synthesis method that leverages the applied intensive condition that you need to synthesize your extensive advantage for your target phase, then you can reliably target various forms of materials under various forms of conditions, under various forms of synthesis methods. So at the beginning, I posed two questions for synthesis and synthesizability. I said, can we understand which predicted compounds are synthesizable? Vladan earlier showed a very nice discussion about basin widths. This is just on top, this is on top of that. Materials have to have large basins, but also, I would argue, they have to be extensively, they have to have the extensive advantage to be synthesized under some condition with an applied intensive variable. And which material synthesis method should I use? You should use the one that has the intensive variable that leverages that extensive advantage. Okay, so there are unsynthesizable metastable materials, and for the ones that you can synthesize, you have to think a little bit about which synthesis method I should use. My clock says 5:56, so I am low on time. I don't really have time to talk about synthesis recipe. We have done a lot of work on this. I'm not going to show this. We published in Nature Materials last year on finding synthesis recipes in sodium cobalt oxide. And here's another paper that will come out probably in the next couple of weeks. That's going to be coming out in a nice journal about modeling sequential pairwise reactions that drive solid-state synthesis. So we also have done some work on synthesis recipes. I unfortunately don't have time to talk about it today. My last thing is that in computational material science, we usually think about going through the synthesis, structure, properties, performance paradigm. We're trying to invert it, right? If you want to invert it, you want to find a material application, and you can use MGI or DFT or hydrophobic DFT to search for structures that give you the good properties for different applications. The last step, the last thing needed to close the loop is predictive synthesis. And so that's my talk today. I'm happy to take any questions from the audience. Here's a bunch of the papers that I talked about today. Thank you very much.
Thank you very much for the nice talk. Beautifully presented. We have one question from Slido. So what role does defect formation energy play in the predicted phase diagram? Do they also affect the Gibbs free energy predicted under different experimental conditions?
Absolutely, absolutely. Anything that you can write a thermodynamic potential for, you can take into account into a phase diagram, right? So, let's talk about defect formation. Defect as in vacancies or defect as in or as in impurities, doesn't really matter. You can formulate the Gibbs free energy as a function of those defects, right? And so if you have defects, then you can make a phase diagram or a Gibbs free energy curve in that direction. Then you can use the intensive conjugate variable, which is chemical potential of vacancies, right? Which can, you can maybe think of a way electrochemically to induce vacancies into your system, or partial pressure of gases or whatever. And you can use that to maybe push your system into another region where you have highly defective or highly impurity rich phases, kind of like what we were showing in the manganese oxides.
Okay, thank you. Another question is, I still do not understand as to why the temperature and solid solution effect not included into the phase stability analysis. Don't you think that will greatly affect its formation too?
It sounds like it's a very great question. It sounds like someone who doesn't do a lot of computation, no offense. temperature effects, of course, are important, but temperature, the conjugate variable is entropy. And entropy in the solid state is very complicated, right? You have phonons, you have growth, and so you have to quasi-harmonic approximation. So in DFT, we have not been able to do phonons very easily at a high throughput scale, not as easily as we can do bulk energies, right? And so a very important objective for our community, maybe in the next 10 years, is to more efficiently produce entropies to consider the role of temperature in these experiments. And in fact, that's something my research group is doing right now. So maybe in 4 years, we can talk about that some more.
We have one last minute. So another question, going back to your example of TiO2, how would you try and predict which ones of the hypothetical structures are synthesizable and which phase diagram would you construct?
Sure. So I mean, TiO2 is one of the very famous examples where, anatase, rutile, and brookite are the ones that have size-dependent phase stability. Now, DFT, by the way, incorrectly predicts anatase as the ground state phase. So there is some other DFT errors in this space. So let's pretend DFT were perfect. If DFT were perfect, there's still this size-dependent phase stability that stabilizes the lowest 3 energy ground state phases. These phases that are known in TiO2 are high-pressure phases. So you see that TiO2, if you made a phase diagram with respect to temperature, pressure, and size, you would capture all the known TiO2 polymorphs. Okay, but maybe there are other axes that we haven't really, deliberately examined yet. Maybe, I don't know, oxygen chemical potential. Oxygen chemical potential, you can reach the Magnelli phases, right? Like Ti509, Ti407. And so, maybe there are other thermodynamic axes that can be used to synthesize other exotic TiO2 phases.
Okay, thank you. Let's move on to the next speaker.
All right, thank you very much.
Thanks again. So we have